Hey folks, good afternoon. We're just going to give it about a minute or two for all the attendees to join in, and we should get started shortly. Thank you. All right. Hello, good afternoon. Sorry, folks, I just had a bit of technical difficulty, but I am connected back again. So apologies for that. So going back, I wanted to just go through exactly what we were going to present today. Today's series are going to be focused on the electrification. So within the entire portfolio, we can accomplish multidisciplinary design when it comes to the electric vehicle. Battery design, electrified powertrain, electronics and electrical systems. We can do attribute optimization, software controls, and packaging and weight. However, for this series, we're going to focus on just two aspects. And today, we're going to be focusing on the battery design aspect. And then on the 30th, we're going to be focusing on packaging and weight and talk about lightweighting. These are one of the two, let's say, bottlenecks right now we face in the electrical series. So for today's session, it's going to be battery design. There are going to be two presenters. It's going to be myself. So my name is Yafa Siddiqui, and I manage the pre-sales team at Maya. My focus and my specialization is on thermal and flow analysis, but now we cover the whole portfolio that's required to analyze your, your engineering device in the virtual environment. And today, joining us today will be Hassan. Hassan, do you want to introduce yourself?
Sure. Thanks, Yafis. Hi, everyone. My name is Hassan Jabri. I work as a technical pre-sales specialist alongside Yafis Siddiqui. I specialize in system simulation, more or less SimCenter AIMSIM. Back to you, Yafis.
Perfect, wonderful. So before we jump into the presentation, it's going to be quite a heavy presentation, and there's a lot of information. But before we jump into it, I thought maybe just go over who we are and what Maya is. So essentially, Maya is an a software-driven engineering solutions company, started in 1980s, specifically, with our origin in the aerospace industry. But over the last 3 decades, we have expanded in every engineering discipline there exists, with 75% of our staff being scientists and engineer. We're very technically driven. So we developed, Maya started with its own software doing thermal analysis of satellites, but over the years we have developed 30 plus modules. So in terms of what we can accomplish, we help in setting up Team Center for product lifecycle management, automation optimization workflows for customers. We are also involved in machine learning and IoT deployment, manufacturing, design, and our specialization in simulation. So we provide a full one-stop shop for creating the virtual product or virtual production of your engineering process. And so, as I mentioned today, we're only going to focus on the battery design. But the big question is, why is battery modeling necessary? Obviously, most of you who are presenting here understand that, and that's why you're available. But I thought maybe just give you talk about some of the top reasons that this is evident more than ever. So first thing is the electrification of transportation. Now every other day, there's some news about some major car producer promising to switch to EV. By 2030, we're seeing that majority of our car sales within California are to be electric. And so this need is driven by, in true honesty, due to the rise of Tesla and its vision for more environmentally friendly transportation methods. Now, we're being pushed to design batteries that are higher power, higher energy density, and even higher efficiency while maintaining reliability and safety. Now, this has led to designers needing to shorten manufacturing time. We need fast analysis of many design variants and fewer time consuming prototypes. Next, consequently, cost reduction is a need. We're talking about design costs, operational costs, maintenance costs. Most importantly, in an all expanding industries, there is a need for innovation to reign, right? This means testing additional chemistries in reaction, wider operating ranges, looking at specific novel processes and materials. So battery design is important. But what are the challenges you face when designing batteries? Let's look at a few of them. But before we do, I'd like to run a poll, essentially looking at what are the biggest challenges you face in validating your design. So on your screen, you have the opportunity of four options. So what is the biggest challenge you face in validating your design? First thing, do you depend on physical testing to validate your design? Second, you might use simulation, but it's usually late in the design cycle, right before manufacturing, where rework is always results in additional costs. Third, you want to invest in simulation, but you lack expertise. As we all know, using a lot of these simulation tools requires expertise, and hence it results in uh, I would say, difficulty for companies to deploy simulation technology. And lastly, you as a company, you solely depend on tribal data to make decisions. What that means is it's most of it is based on engineering intuition or past data. So I'm just going to give another 20 seconds for folks to put in their polls, and I can see the folks that have voted. So I'd recommend you to just put in some data based on your experience. Perfect. I'll give you guys another 10 seconds and let's close. All right. So might as well share the results. So what we see right now from the poll that we have taken is that majority of the companies, they want to invest in simulation. They see the value of simulation in reducing costs as well as driving innovation, but lack the expertise. And the other thing is, you do use simulation, but it's late in our design cycle. And then finally, the two, that is, you depend on physical testing and validated design. And lastly, solely depend on tribal data to make decisions. So this is exactly what we are seeing when we talk to our customers and when we speak to our customers regarding simulation technology. So hopefully by today's presentation, we will shun away the aura of why that simulation is difficult, as well as talk about how we can implement solution technologies that are easily early in the design stage than late in the design cycle. Perfect. So moving on forward, I want to just bring up some of the challenges that are faced by modeling battery designers. First thing is, we have seen that there is no streamlined simulation tool available to address all the challenges of battery design. So when we talk about battery design, we're going to talk about from the cell microstructure, the unit cell, studying the unit cell in the battery pack with thermal management system, as well as studying the whole battery pack with its thermal management system in its engineering, uh, real world behavior essentially. So there is no one solution set. There are barely any solutions essentially available for battery simulation specifically. And even those that exist, they're disconnected over the design process of the battery system. Another big challenge is the dependency on costly and time consuming prototype driven design and physical qualification tests for thermal validation of components. Another thing is physical testing stifles the ability to explore many design variants in development of, becoming a barrier to innovate. So another common challenge is setting up simulations for thermal validation of battery packs and electronic systems. These contain thousands of parts. It's time consuming, it's difficult, and it's error prone. So today we will look into the Siemens solution that streamlined the design of a battery virtually from the cell structure to the single cell to cells in the battery pack and batteries in full systems, while using simulation to reach your optimum design based on your objectives and constraints. So let's have a look at the engineering process for battery design and the Siemens solution offering. So first, in terms of the battery design, when designing batteries, the first step is pre-sizing. You want to understand what are the required voltage, the power requirements, and then that's when you select the battery technology. If you're using lithium ion cells, do you want them in stacked or cylindrical? Then you do some sort of battery requirement validation. Does that given power, does that given set work with your given system? Let's say you are using a battery pack for an electric vehicle. So does the motor requirements meet the power that's generated from the battery pack, right? Next, once you've got a some sort of sizing perspective, there are two specific forks. One is where you virtually analyze the battery with its thermal management system, making sure that it is able to sustain all the duty cycles. And then the other important aspect, which is not most discussed, but is a big issue with battery packs, is their battery management system validation. Is your battery management system that you've generated optimizing the usage of your battery power to the given problem statement you're trying to resolve? And then the other issue is like you still need a lot of physical tests to validate some of your simulation parameters, and there's a lot of simulation parameters that are unknown and that you want to extract from your experimental data. So this is a general engineering process for battery design. And so within the Siemens portfolio, we have an end-to-end process to from pre-sizing all the way to setting up your battery requirement validation, doing the thermal management in 3D and understanding its performance with the cooling system, but also looking at the battery management controls loop and analyzing that within the thermal behavior and the efficiency and looking at the efficiency of the battery with regards to those controls, right? So as we mentioned, this entire workflow is available within the Siemens Digital Innovation Platform. Before I jump into the solution, just wanted to give a quick history to the Siemens Innovation Digital Platform. So over the last 11 years, Siemens has invested $11 billion in key acquisitions, essentially to position itself as a leader in next generation engineering. What it did is, instead of leaving them as independent companies, it brought them together into one single platform. So what does this platform look like? This platform is a multidisciplinary platform consisting of specifically 8 engineering domains. On the left-hand side, you have everything to do with mechanical design. On the right-hand side, to do with manufacturing. So we're talking about mechanical design, software delivery, manufacturing planning, automation, and this entire platform is managed with Team Center or PLM kept in mind. So today we're just going to focus on the simulation and test. And the simulation and test portion of this platform is called Sim Center. So Simulation Center, Sim Center. So this platform essentially allows you to do multi-physics simulation in a cost-effective manner. We're talking about CE for 3D simulation, systems for model-based system engineering, but you can also connect it to physical test to do combination of connecting your system solutions to physical test data or your physical test data with your 3D data to do correlation. But one of the key aspects of this portfolio is exploration and analytics. What that means is that we use SimCenter not only to just analyze your design to make sure it meets the requirement, but to create the best design based on given constraints and your objectives. So we're going to be using SimCenter to explore how we can resolve the problems that we face in the battery industry. So within the SimCenter portfolio, we're going to talk about the battery modeling process. So first things first, when it comes to battery modeling, we can within the Siemens portfolio analyze a wide range of length scale, and this is perfectly appropriate as studying and designing batteries is a multi-scale problem. So we're going to start small and move up from there. First, our software portfolio can start all the way with studying the microstructure electrochemistry. The engineer can here study in 3D the effect of the electrode morphology on electrical performers. So this tool is addressed to material manufacturers and cell designers. Then, moving on, we go to the cell level. Our solutions have the unique capability on the market to allow cell designers to build a digital twin of the cell by configuring with high fidelity each component of the cell design. So this design is then coupled to a performance model to test virtually the cell conditions in various conditions like drive cycle, pulses, arc test, oven test. So once you've done your single cell, to study packs and modules, we move to the next level. We build and analyze the complexity of the pack with its thermal management system, leveraging the cell design we created in the previous step. So it's a streamlined workflow, and with a few clicks, we can set up batteries consisting of hundreds of cells. Here we analyze the thermal behavior while understanding the highly coupled behavior of the pack's electrical performance as well as the surrounding environment. Now, finally, we need to study the full system, co-simulation between the system simulation tools introduced in the last session to bring even more realism in actual drive cycles applied to the pack. So essentially, we bring a full breadth of solutions within the battery modeling process. For today's presentation, we're just going to focus on these three aspects. As you know, this is mostly focused towards battery manufacturers. Here, we're going to start from, let's say you've already bought your battery from a third supplier, and then you set up your main aspect is creating the battery pack and then the system design. For today's presentation, I'm going to focus on the virtual cell and the battery pack, and Hassan will focus everything that is related to system designs. So before we jump into the session, I will or the workflow demo, just give a quick overview of what it's going to look like. We're going to start from a unit cell. We're going to leverage that same data to build a 3D model, and then we're going to connect the 3D model to the system to analyze the performance based on actual performance data. So we're going to go through the demo in terms of how we set up a simulation. We start with the cell design. And then once we build a cell design, we from a unit cell, we create a battery pack. This is where we set up the physics, set the mesh here, as well as not only analyze the thermal and flow behavior, but also the electrical performance. So if you want to look at cell voltage density as well as a key parameter, or even your state of charge, and then we're going to analyze. But the key thing, as we mentioned earlier on, it's not about just analyzing; it's about optimizing to get to the best possible solution. So first, how is this different from what we have done? So when designing cells, let me just talk about, before we talk about the unit cell, I just want to take a step back and talk about when designing cell, traditionally what, in simulation, the properties of the various chemical components are communicated on data sheets from battery manufacturers, who then create a cell and they attempt to meet the criteria that are specified. So within the Siemens portfolio, we have a platform that can combine the electrochemical properties of varied electrode and electrolyte materials and accurately model their performance against the critical criteria. So this reduces the gap between the laboratory and implementation considerably. So in this, for this demo, I'm going to just quickly characterize the geometry, sizing, the materials, and test the performance of the cell thoroughly. And we will also set the data for a load cycle. And so let's just quickly jump into this tool. So our solution allows the user, with great accuracy to create the digital twin of the cell, the geometrical details, all the components that can be precisely defined. Here we're going to create, lithium ion batteries. Those are the most popular of two shapes, cylindrical and stacked configuration. Here we'll be creating a lithium ion stack battery cell. So in this solution, a default geometrical representation is automatically created, which can be easily edited. Other than building a geometrical representation, we can set up the material properties as well as calculate the associated costing parameters for our design. And then we can also couple the geometry to performance models. So these are physics-based or equivalent circuit models. In this demo, we will simulate the cell performance under a discharge cycle. See, the current rating of the cell is 10 ampere hour. A discharge cycle of 10 amperes in 1 hour will be set up. So note this tool provides the ability to set up any conditional pulses or duty cycles you would like to run. So it's not only a single test cycle, but any combination of those duty cycles. The solution also comes with an aging model to study the effect of calendar and cycle aging by resolving the mechanism of solid electrolyte interface growth. You can do thermal abuse tests, oven test or arc test. The model can be configured to predict the point at which the cell enters in thermal runaway. So when what we did was just create a physical representation of cell design under a discharge cycle. So let's just move to the next step. So in the next step, we will be taking the cell design and leveraging the geometry and material properties to develop a 3D model of our cell. So in the previous step, we only took a 1D representation of the model. It does not have any 3D representation. So generally, the user would have to manually import the data from the 1D to the 3D model. And this is time consuming and error prone. Like, how do you set up the properties for the electrolyte, the cathode, the anode, the physics based modules? But however, there is a streamlined workflow to take that 1D representation and create a 3D geometry within our workflow. So let's just see how that's done. So the multi-physics CFD tool that we have has a dedicated workflow for battery modeling for simulating the electrical and thermal response of a battery over the course of the load cycle. So activating this workflow is just a matter of a few clicks. The added value of this workflow is that it leverages, as I mentioned earlier, the single unit design we set up moments earlier. We can use the design to not only analyze the single cell's thermal and electrical response in 3D, but we can use it to create a full battery module and analyze them. I'll come back to that later in the demo, but first let's just model a single unit cell, baby steps. So the first steps of the battery module generation process is building the geometry and the connector parts. Here we're going to do this with the data of the single unit cell with no other user input required. As you can see, the battery module has been imported in 3D with the material properties also in place. So we will set up the battery module in a few steps. Here we're just starting with one cycle and then we'll expand it to, let's say, 3 cells in series. So once the geometry generation is complete, we will assign them to regions. This is where we define the boundary conditions. This process is automated and is done with one click. Next would be setting up the circuit that is connected into a battery to, let's say, a discharge cycle that we had previously created. More than just simulating the thermal loads by the circuit tool, it has a circuit solver to connect the battery modules with the electrical loads. So finally, the final step here, we're just importing the program file that enables us to connect the circuit to the duty cycle that we had created in the previous step. So other than just repeating myself, is bit, other than just doing the thermal analysis, we're actually solving an electrical circuit in this given module. So the final step in pre-processing the domain before adjusting the solver parameters would be meshing the domain, right? And usually this is the toughest part of creating any 3D simulation model. However, using the inbuilt battery workflow, we can do this within a few clicks. Next, we set up the solver settings, you know, so right click, create the mesh, and the mesh is generated automatically. And all you can do is, the next thing, we set up the solver settings. Here, we're going to set up a simulation time of 90 seconds. I will going to execute the meshing process, observe the mesh quality, and then we can see is that the mesh is well defined. And the workflow for the battery setup is not only limited to pre-processing, but also post-processing. So we're just going to wait for the mesh to execute and be able to actually analyze and visualize the quality of the mesh that is generated. And so note that for the mesh generation process, it was just a one-click step process. We right-click and generated a mesh without any user input. So the reason and the ability they can do this is because it has best practices already fed into the process. Here we're just going to create some post-processing scene to visualize some battery parameters. As you can see here, there are given functions that are automatically inbuilt within the tool, and these functions are predefined, and these are essentially the functions that any battery engineer would need. Here we're looking at the battery's volumetric heat, and one key thing about SimCenter Star CCM Plus is that you can essentially analyze the solution while it's running, and that's the reason why we're creating post-processing features prior to even running the solution, so that we can analyze the solution while it's running. So we're going to look at some plotting data as well. All right. So we're just going to run it and analyze the solution. So here's some, this sort of setup can be done in less than 5 minutes, but now we only did it for a single cell. Let's try to go back and repeat the entire process, but uh, for a series of 3 unit cells. And we'll quickly run through the process and show how easy it is to do from a user perspective. Note to all the folks out here, if you have any questions, please don't hesitate to drop in the chat. We'll answer them now, or we'll take our opportunity. We'll take some time after the session to answer them. So in the previous setup, we created for a single cell. Now we want to create a battery pack of 3. So all we need to do is, replace the process of a single cell to 3 cells, set up, import the connectors that we would like from a given geometry, and how the 2 tabs are going to be connected. So this workflow is streamlined from one step to the next. And now we're generating the battery packs. As you can see, now we have 3 packs set up in series. And right click, create the mesh, and set up the regions as we did in the previous step. It's quite easy to do. So basically, I'm gonna skip this process just because we have a heavy presentation today. But essentially, I'm just repeating myself of what we had done earlier. Is we just add the new parts and rerun the simulation. But looking at this given workflow, we understand that you need Battery Design Studio and need to import and have a great representation of that single unit cell. But generally speaking, for a lot of battery designers, they don't necessarily have a lot of this information, especially during the pre-sizing phase. And we understand that this workflow could be sometimes difficult for users just starting out. And maybe they just have a 0D model of their battery where they just know the resistance of their electrodes, or some sort of simplified workflow. So beyond this workflow where we take a full detailed representation of the unit cell, that's in the case you have it from your suppliers, we also have a second workflow within Star CCM Plus. So I'm just going to quickly run through the workflow. I'm not going to run through it visually, but I'll just go through the steps that are required. So what you can do is, once you've imported, in this case, in this given module, we generated the unit cells and created the battery pack. But what if you have the CAD geometry of your full battery pack already set up in 3D, and now you want to represent those 3D units as cells? So we have the capability first importing the information directly from battery design studio, but also from third party source that could be your supplier. And in this case, we run an RCR 0T model. I'll just quickly go through some of the what the RCR 0T model is. It is a representation of a battery with a resistance model where the resistance of the electrolyte, the electrodes are given by just a resistance capacitance model. It's quite simple, and it's good to get an initial sizing of your battery. So you take that RCR model, then you configure it and assign it to your parts. You can create a circuit with a circuit modeler directly, and then run the analysis with not only just analyzing but also optimizing. So this process is obviously 10 times faster because the fact that you don't have to use the battery design model in detail, but this is a great workflow for your initial sizing. But up to now, we've just analyzed the design, but we want to focus on the key thing, that is design exploration. And this is typically the holy grail of simulation. Validating a design is generally the stepping stone, and at the end of the day, getting a better design quickly is typically what people are gunning for when investing in simulation. And this is what I'll be showcasing now. So within this battery pack geometry, you have a cooling channel that is parameterized. So one of the key aspects of our tools is it's well connected. So CAD and simulation are bidirectionally associated. What that means is any change to the geometry in simulation will adjust geometry in CAD. And so what that enables us to do is take the parameters that we build our CAD model and drive change. So in this case, we're changing the channel, the number of channels, the number of S bends in the channel, and what we can see is also adjusting the thickness of the channel. So this is done with a few clicks because it's in, the entire workflow is well connected from CAD to mesh to post processing. And this is what we want for our customers to be able to do, is to drive innovation through simulation. So I'll quickly run through the solution and show you the results of this design study. So the objectives was to minimize the pack weight and minimize the pressure drop within the coolant channels, with given constraint that you had to ensure that the max temperature was less than 60 degrees and the max temperature difference less than 3 degrees Celsius. So here we're trying to decrease pressure drop as well as decrease weight. As I can see, the solution automatically iterates through all those parameters, looking at the inputs and outputs and running through a genetic algorithm that solves for one cost function instead of multiple cost functions. So running multidisciplinary optimization becomes quite efficient. And so this simulation was run on 3 days on 120 cores, and within 3 days we were able to get a more optimum solution. Uh, so before I jump in, one of the key aspects and one of the things that we haven't discussed, and I'm sure many of you guys have heard about exploding batteries, and that's because of a condition called thermal runaway. So that's when current flowing through the cell or battery or charge or causes the cell temperature to rise, increases the current, which increases further rise. This often leads to explosion batteries. And I'm sure that we've all heard of the Samsung phone and all those issues that were faced. So you can understand that this is a big concern within battery industry and can cause a lot of costs and associated damage to the reputation of the company. So modeling thermal runaway, as you can understand, is very complex problem because you want to understand gas expansion, this combustion, there's a combination of that features. So that pretty much can be handled within our simulation tool. So we can model as you can see over here, thermal runaway in various capacities, from single models where we're only looking at the evolution of the gas based on a chromatographic test of the composition. But we can also then look at simple understanding of thermal behavior when it exceeds thermal runaway, ensuring that the casing can ensure can sustain the stresses associated with it. But we can also then model the full combustion of the thermal runaway simulation within our solutions. So before I pass it on to Hassan to take over the next part of this presentation, what I want to do is run through the second poll question. And so Earlier on, we did talk about some of the challenges within validating your design, but I'd like to understand now, what are the challenges that you face in battery modeling specifically? So many of you guys are battery modelers available in this session. So I wanted to understand, what are the biggest challenges that you face? You know, is setting up the simulation of the full battery module with the with all the different packs an issue? Give at this given stage, we know that a lot of customers just apply heat loads there. Do you have an issue modeling the electrical and thermal performance simultaneously? Generally, we only study thermal performance or study the electrical response, but the other issue is that you don't use simulation at all, and you depend on physical testing. And this is very common within the battery industry, just because modeling batteries are very complex. There are multi-physics problems. And lastly is like, you're not involved in batteries, and maybe you're trying to understand what it takes to get into battery space, but even if you're not involved in the battery space, understand that this technology that we're showcasing is not only limited to the battery world, but to any engineering problem. So let's give it a minute, or let's give it another 30 seconds, I'd say, uh, before I close the poll. And just another reminder, if you have any questions, don't hesitate to drop them in the chat. All right. Let's give it another 20 seconds and we should be good to go. And I'll be closing the poll. So let's quickly look at the results of this specific poll. So the question was, what's the biggest challenge you face in battery modeling? And the biggest response is setting up the simulation of the full battery module. And I completely agree. This is considerably a tedious task. You have hundreds of cells within a battery pack. How do you model each individual cell? You can find yourself for 3 days just clicking buttons and selecting the electrodes, anode, cathode, and the heat load associated with it. And so modeling the electrical and thermal performance, that's also something that's quite difficult to do. And also lastly, you don't use simulation, but depend on physical tests. So from this poll, you can clearly see that the solutions that we provide helps resolve these challenges. The first thing, setting up the simulation with the battery pack, quite easy to do. Modeling the electrical and thermal performance, it's inbuilt into the tool. And lastly, if you do base yourself on physical tests, know that the technology that we provide is automated, it's easy to use, and does not require expert usage. So now I think I guess everyone's tired of listening to my voice. I'm going to pass it to Hassan to cover the next portion of this presentation. Hassan?
Perfect. Thank you, Yafis. Um, Perfect. So now that we've analyzed, as Yafis was showing us, how the battery as an individual component was modeled at a given current cycle, like with a steady load, although these conditions were based on a given profile, like in real life situations, the profiles are constantly changing. The batteries are part of a complex multi-domain systems that contains various systems depending on different physics. I mean, as always, the challenge we face is how do we virtually verify if a complete system in a virtual environment and not just like individual components. So this could actually be accomplished by multi-physics system simulation. We do the multi-physics system simulation using our software SimCenter AimSim, which I'll do a quick refresher on what SimCenter AimSim is, what is it capable of doing, and then I'll dive a bit deeper into some detailed application examples of the software. So in order to start, AimSim is an integrated scalable system simulation platform. It allows users to do multi-physics simulations that combine different physics like electrical, thermal, hydraulics, just to mention a few, of course, in order to virtually assess and optimize an entire mechatronic system's performance. The tool can connect to more detailed analysis tools like fluid modeling, StarCCM+, for instance, or even FEA analysis for structure analysis. Let me give you a quick introduction on SimCenter AimSim. So as previously mentioned, AimSim is a system simulation software. How it works is that we use multi-physics libraries in the software in order to create models. These libraries are either physics-based or they're industry-based. Physics-based libraries vary from thermal, mechanical, hydraulics, even thermal hydraulics, electrical, but the industry-based libraries, they vary from electrical storage libraries, battery libraries, electrical motors, and many more. On top of AIMSIM being a very scalable software itself, having all these different libraries, AIMSIM is an open environment, meaning that it can very nicely connect to various tools and softwares, like a couple of examples that we're going to be looking at in today's presentation. So in order to do that, let's dive a bit deeper into the battery analysis and electrification in AIMSIM. When it comes to battery analysis, we would always start with pre-sizing our battery pack. We start by defining a requirement or even evaluating an architectural concept, let's say, if we already have a battery design. We do that given the various tools and functionalities that AIMSIM has, which allows users to import their data sheets for the batteries, import, for instance, charging discharging cycles, and then we define these data sheets in AIMSIM in order to have it in a virtual environment. So this kind of modeling yields great outcomes that users always look at important results, such as, for instance, aging of the battery pack, the state of charge of the battery pack, and even the thermal expansion of it. But most importantly, we're actually capable of integrating this battery or this battery pack that was defined or pre-sized initially in a full system. So technically speaking, we can look at that battery pack not as an individual component, but integrated in a full, for instance, electrified powertrain, like the example we see here, where the battery pack is integrated to an electrical vehicle, or it could even be a very simple test bench that tests the battery's voltage and currents, for instance. So for that, in the upcoming example, we're actually going to be looking at a 1D, 3D co-simulation between Star CCM Plus and AIMSIM. In this example, we're modeling a thermal management system of an electrical battery pack, and then we're validating its performance while the vehicle is actually in motion, while the vehicle is moving. The input here is the velocity of the vehicle, which is then used in order to determine the cooling performance of the radiator. So just to get a tad technical here, the cold coolant fluid that is coming from the radiator is actually being fed into the battery pack, and then the hot coolant that is coming out of the battery is being fed back into the radiator for it to be cooled. And now that we're looking at this model, we're going to be looking how does this co-simulation work from a software perspective and how intuitive it is to technically perform it. So this is the AIMSIM model. As you can see, there is a TCP port on the left side. That is going to be your connection to the CFD tool, which is RCCM+. It's as simple as like setting up a port and then having inputs and outputs connected to the radiator right there. So in AIMSIM, we represent the entire cooling system. We provide temperature and mass flow rate boundary conditions at the inlet of the battery pack. But in StarCCM+, which is the software we're looking at right now, we calculate the heat flux from the pack into the coolant, and then we provide the coolant's outlet pressure and temperature back into AIMSIM. So in Star, we leverage the same battery workflow in order to set up the simulation. The mass flow rate input is going to be the variable that is fed by AIMSIM, and then the pressure outlet is going to be fed from Star into AIMSIM. To set up this connection, as you can see from here, in Star CCM Plus, it's actually nothing but activating the AIMSIM workflow and then setting the correct port numbers in order to match the port between Star and AIMSIM. So now that we're doing this, all that is left for us to do is verify some settings, and then once that is completed, we can run the simulation. A quick note I'd like to mention here is that based on my experience, we've seen companies perform this on other solutions that always require in-house scripts to do so. These scripts are usually valid for a given release and they need to be constantly updated. We were actually able to achieve the co-simulation that you're looking at right now with our in-house built-in capabilities with an absolute no need to use any scripts. Just a simple co-simulation like the one you see right there. And now that we're on the simulation, we can now look at the results of both the 3D perspective and from the 1D perspective. On the left-hand side, we can look at the results from the 3D perspective from the Star CCM. Oops, I want to run video. Right there, from the left-hand side, that's Star CCM Plus results. And then from the right-hand side, we can look at the 1D results that we got from SimCenter AIMSIM. In the previous model, we've seen a fairly smaller system that contains the thermal aspect of an electrical vehicle. In this example that you're looking at right now, we're looking technically at a more detailed model that incorporates different systems of an electrical vehicle, such as a full cooling AC loop, a battery control unit, and even an electrical motor. Such models help immensely with one of the main challenges of all electrical vehicles that we've seen, which is the development of the battery component, and then, most importantly, the integration of this battery component to the full vehicle. Physically developing and training these new compositions is a very expensive and a resource intensive process that only large organizations and very well funded university laboratories have the capabilities to perform it. That's why AIMSIM has all the capabilities that is required to model all these big systems like the one you see here in a virtual environment. And then once you have this model in a virtual environment, it allows users to assess the performance of their components individually to start with. You can look at the battery, what's happening in the battery, electrical motor, safety control unit, etc. But most importantly, you're also assessing the performance of your system as a whole. So you're checking what happens if I increase the voltage in my battery, what's going to happen with my drive cycle. So you're assessing the performance of your full system. And that's very helpful, especially early in the design stage. So in this, back to this model, the electrical drivetrain efficiency that you see in this model, all the way from the battery to the wheels, is related to obviously, I mean, many different factors, but most importantly, we're going to be looking at is the performance of the lithium-ion battery that exists here, which in return depends on the properties of the electrodes and the electrolytes. So another important parameters that we're looking at here would be the voltage characteristics, the state of charge, and then the thermal load of the electrical vehicle. In order to do that, the model that you see right there was eventually co-simulated with Star CCM Plus and Battery Design Studio in order to have a full analysis on our model. In Star CCM Plus, we have a battery simulation module that supports the AIMSIM co-simulation. So you can use technically AIMSIM to model the full drive cycle and then use the Battery Design Studio software and Star CCM Plus in order to provide the battery model. When you run the simulation in AIMSIM, it passes the voltage and current requirements to Battery Design Studio, which then performs internal modeling for the battery based on the parameters that it got from AIMSIM. And then it would return the results back to AIMSIM. So in this case, you're actually looking and analyzing the battery from a very detailed perspective in BDS, which is Battery Design Studio. Also, we're getting crucial thermal analysis results coming from Star CCM Plus. We're putting all this together and analyzing it in a full drive cycle as it exists in real life in AIMSIM. So we're technically having the best of both worlds. I understand that so far we've more or less focused on the virtual prototyping of batteries. We understand that getting these material data for the batteries and using them in a simulation platform is somehow a challenging process. So that's why we leverage using the ROM builder, which is going to be explained now. The ROM builder, ROM stands for Reduced Order Models. Uh, Reduced Order Model Builder, or the ROM builder, is actually an application or a tool that exists in AIMSIM. It allows users to represent the performance of their battery unit using machine learning and AI algorithms. So how it does that is by initially defining the system's requirement, which for instance, they could be a simple voltage or a current response to any inputs. Once we do that, we then move to the actual training of the data that is imported into AIMSIM in the ROM builder. This data could be, again, charging, discharging cycles, performance cheats, or anything else. Once this data is actually trained in the ROM builder, we would extract the reduced order model, and then we would use it in our simulations. The benefits of having a reduced order model could vary a lot from, to start with, running simulations way faster than the tribal or the past data. We can run the simulations, or we can model actually without even using material properties. And most importantly, we can also have our model ready for real-time processing if that was ever a requirement. So we could have our model ready for model in loop, hardware in loop, and software in loop real-time processing if that's a requirement. So from here, to be respectful of the time, I'd like to pass it back to my colleague Yafis, who is going to discuss battery modeling processes in the simulation workflow. Back to you, Yafis.
Perfect. Wonderful. Thank you very much, Hassan. So far, we talked about in detail the unit cell representation, creating the battery pack, and then also the system design that was covered by Hassan. But it's also important that, we note that this given workflow is well connected, that in the sense that any data that's created in one process is leveraged, reducing redundancies and increasing efficiency. And so, we talked a lot about the battery process, but I want to talk about some success that we've had with using these solutions. So I'm going to run through two success stories. We could run through multiple, but within Maya, we essentially have a conversation with any or every battery manufacturer that we can get our hands on, is because we believe in our solution. So one of the success stories that I'm pretty proud of is with the Lion Electric company. They worked with Maya with us to identify the best digital analysis tool for optimizing, battery design for their zero emission school bus. Just another thing, I pass by the Lion Electric factory every now and then. So this is basically based in this company is based in Quebec, and essentially what they wanted to do is create the electric school bus, as you can see here. So we were able to help create better designs and opportunities for innovation and essentially create a forward-thinking vehicle design. They were able to accurately evaluate safety, energy consumption, passenger comfort, and vehicle performance all through simulation, reducing costs and driving innovation. Another interesting example is with a company called Gibbers. So they design outdoor recreational vehicles, and using the solutions that we presented today, they designed a novel coolant-based thermal system to optimize for electrical stress and aging. So on the video to the left is what you'll be able to see in various variation of battery volumetric heat for a drive cycle, for passively cooled pack, and on the right-hand side, you're going to see the temperature rise. So there are many household names that we work with within the EV and battery industry, and Maya as a company has a lot of exposure to understanding the problems they face and providing quick and efficient solutions. So before we call it to the end of this presentation, I'm going to run through our last poll, which I'm just going to showcase in a second. And so the last poll is basically a very broad question. Do you run multi-physics or cross-domain analysis? The question is like, do you run fluid thermal structural analysis, but all combined within one given simulation? Or the first option is, yes, our solutions are strongly coupled, so fluid structure interaction, two-way implicit methods are employed. The solutions are weakly coupled. That means you do the structural analysis, take the structural loads, and then apply it on the thermal analysis, or vice versa. But it is, there's a transfer of data involved, or there's information passed from one division to another. And last question is, no, we do not perform multi-physics analysis. So I'll give you guys another minute to answer the poll before we close it. All right, I'll give it another 10 seconds before I close the poll. Perfect. All right, so I'm going to quickly share the solutions. As expected, what we see is that you do run multi-physics simulations, but these are weakly coupled, and they are weakly coupled because it's very difficult to find solutions that can transfer the data efficiently between one physics solver to another. However, as we've seen, the solution that we provide are highly coupled and allow us to do multi-physics simulations in quite an efficient manner. So let's quickly, conclude this presentation. So before we jump into some of the next steps that I'd want you to take, what I want to, basically talk about throughout this entire presentation, our entire engineering process can be streamlined with validated industry-specific workflows. But today we focus on battery simulation, but we have a wide variety of engineering workflows to help increase in proficiency, reducing costs, and driving innovation. Beyond just providing the products, Maya has a multidisciplinary team who have vast experience in resolving technical challenges in all industries. We provide an engineering alignment to help establish an engineering process strategy to maximize your business benefits and reduce implementation risk, essentially providing that catalyst you need for business change. We've done various simulation assessment. One of the assessment Maya proposed recommendations to reduce a customer's overall design process from 18 months to under 12 months, while positioning them for growth in their focus market. So we're not just focused on battery, but through a physics multidisciplinary engineering solution. So, like as I mentioned, today, we can provide multiple physics solutions beyond thermal flow and electric. We can talk about additive, durability, and structural, and that's where I want to segue to the next session that we're going to have today. As we talked about electric design, but we want to talk about also packaging and lightweighting. Yes, you can create these battery packs, but can whenever we look at battery packs, biggest issue with increasing the energy density is increasing the weight. And so on the 30th of November, we're going to have Martin from GRM Consulting basically talk about lightweighting. So just a quick establishment of next steps before we jump into the question session. I just wanted to let you guys know that. Oh, apologies, I went all the way to the start. Anyways, so what I wanted to cover is that for any sort of complementary readiness assessment, please don't hesitate to email us at info@mayahtt.com. We're going to send you a survey right after uh, this session. Please review the survey, and the recorded presentation will be provided. And for any other session other than this, in the next session, it is on our website. So that's mayahtt.com/events. And that's mayahtt.com/events. And so, lastly, before we end this session, I thought I'll look at the questions. We have a few questions that have come in. Please don't hesitate to bring in any questions that you'd like to cover. Let me just open these questions. Give me a moment. I'm just having some issues here. Oh, there you go. All right. So one of the questions that we've received is, we have issues with the controls of the battery management system. Can we model that? Yes, absolutely. So the beyond just analyzing the thermal management system, looking at voltage and current, we can model the battery management system within its controls in place. Right. So the next question is, how does the ROM or reduced order model extend to other applications other than battery design? Excellent question. So earlier on, Hassan showed the reduced order model. Do you want to answer the question, Hassan?
Sure. Yes, absolutely. So reduced order model is in that specific application we were referring to battery design, but it actually could be any model that we can take in data coming from any source, whether it's a simulation data, whether it's test data, or whether it's any kind of data. It can be imported into the ROM builder. It can be trained. It can be used then in a simulation workflow, whether it's a battery design that we're working with, or with an electrical vehicle, or anything else. So the main purpose of actually having the ROM builder is to have a tool that allows users to have their data coming from any source back to AIMSIM, trained in AIMSIM, and then back to that external source, whatever it came from. I hope that answers the question.
Perfect. Wonderful. So folks, uh, if you have any other questions, please don't hesitate to drop that in. And in case some of the questions come up after the session, please don't hesitate to email us at info@mayahtt.com. Um, Other than that, I hope to see you all for the next session on the 30th of November. For more details, please go to mayahtt.com/events. For those who have attended, we will provide a survey as well as a recording. Other than that, I hope you guys have a wonderful day and hope you guys have a great weekend coming through. All right, take care, guys.
Thank you, everyone.